Okay, everyone, it's time to start. Time to start. And we'll just talk for a few minutes. Well, the screen is empty because of technical difficulties, which should be repaired shortly. So, what we're talking about today is chapter 16, so everybody turn to chapter 16, and we're going to be talking about sample surveys. Sampling. Now, we take a sample, and we take a sample survey when we want to find out something about a population. If we want to find out something about the population, like you guys are a population, stat 100. Well, when I give you a survey, I don't have to take a sample because you're a small enough group, and we've got great survey tools that I can survey each and every one of the 1,100 students enrolled in this class. So I'd take a survey. But let's say let's say the population was much bigger. And it would be too expensive, like the whole country. I wanted to find out something about all US adults, let's say. Well, it's way too expensive to survey everybody. We only do that once every 10 years with a census. So what do? We take a sample out of the population, and from our sample statistic, let's look at our terminology here. You see where it says terminology? From our sample statistic, we make an inference about a wider population. And in fact, there's probably only one word out of that terminology. There's 1, 2, 3, 4, 5 words that you might not be familiar with, and that is parameter. The parameter is a numerical fact about the population that we want to estimate, that we want to find out about. So we estimate it with our sample statistic. Easy to remember that statistic and sample go together. They both start with S, and so we have a statistic, and from it we estimate a population. Shh, you're right here in front of me talking. That's not a good place to be when you want to talk. Okay, like right in front of my face. Hi. Okay, so what is a parameter? I'm going to ask you guys.
Isn't it like the distance around?
No, that's the perimeter, not a parameter. Okay. I asked her, what's the parameter? She said, oh, isn't it like the distance around? No. A parameter is the fact about the population we're trying to figure out, okay? And we estimate it by a sample statistic. Okay. We're not in geometry class, this is statistics. All right. Now, what's the best way to take a sample survey? What do you think the best way to take a sample? What's our goal? Our goal is to have the sample as much like the population as possible. If I want to find out something about the entire population, like what percentage of the people favor gay marriage, for example, that's a timely topic right now because the Supreme Court's talking about that. Let's say I wanted to find that out. Do you think I would just sample only gay people? No. Oh, it's done? Cool, all right. So let's go, well, I'll wait a bit until it warms up. So we wouldn't do that, we'd sample the whole population. If we want to find out what the whole population thinks, we'd take a sample from the whole population. We'd want the sample to be as representative of the whole population as possible. If we just wanted to find out what gay people think, we'd want it to be as representative of what gay people think, right? So what's the best way to do that? What is the best way to get a sample that's representative of the population we're interested in? There's a number of different options. Where's our notebook? I just had it in my hand. Oh, thank you. I need you around my house when I'm always like leaving things. Where is it? Okay, so the main idea, the sample should be as representative of the population as possible. That's in bold right across the notebook. Now, there's three options, three ways, three basic categories, broad categories of the way that we could sample from the whole population. The most intuitive one, the one you might think was the best way, is to hand-pick the people so that they're as representative as possible of the population as a whole, particularly on the characteristics that are relevant to us. You know, if it was a political poll, we'd want the same percentage of Democrats and Republicans in our little sample as are in the population as a whole. So hand-picking them seems like the best way to ensure that, right? That's called quota sampling, when you hand-pick. And that's the way they used to do all surveys. Pollsters would go around door to door, and they would have they'd be assigned particular blocks that represented the demography of the whole US. You know, you have to go, and that's how they used to do it. But within those particular neighborhoods that they were assigned, they would actually have some choice about who to choose. A quota sample always allows the interviewer or the pollster some discretion, some choice, not only in forming those broad categories, but also in picking the particular people within them to survey. So there's human choice involved always. Any problems with that, do you think? What? Anybody? Anybody? What could be a possible problem with that? I heard a lot of people say, yeah, there's problems. Bias, absolutely. Does this sound familiar? Does it? What is this? Is this like a deja vu for people right now? It should be. It should be. Think about it some more and we'll talk about it. But yeah, it's very similar to something we've talked about a lot before. So she said bias. What do you mean by that? Anybody want to elaborate? Well, I'll tell you a story that's actually kind of interesting. The political pollsters, before they knew in a more objective way to poll that would eliminate selection bias, did exactly this. They went door to door and they were told, to poll, maybe pretend I'm a pollster, and my job would have been to maybe poll people within a certain income bracket in a particular neighborhood. But within that neighborhood, I had some choice about which house that I'd go knock on. So I'd be going up and down the street looking for, I have to be on this street, and I have to have X number of men, X number of women, X number of Democrats, X number of Republicans, maybe something like this. But then I look around and I have a choice of which house, and I can knock on any door. And what happens is I'd probably, and most people, pick the prettiest house on the street, or go for some subjective feeling about that. And when people did that, in the pre-election polls, what happened was, who do you think they favored, Democrats or Republicans? What? Yeah, how'd you guess that? He said Republicans. They always favored Republicans. They were right most of the time because they weren't off that much until 1948 when they were tremendously off. But it was always favoring the Republicans compared to how the election really turned out. Why'd you know it would be Republicans? They live in white big houses?
I don't know, you said pretty houses.
Pretty houses, yeah, richer. Republicans tend to be richer, yeah. Yeah, that's true. So they nixed that. Now let's see, we're gonna go to the document camera. We got everything back, and we can look at it. Okay, so where are we? We are right here. We should give a hand to the people who fixed that. Okay. What would Stat 100 be like without technical difficulties? It's hard to imagine, right? Okay, so now let's fill in what we've said. All right, quota sampling. We said that this right here is when the interviewer gets to choose who to survey. Within each quota category. It's not bad to have quotas as long as if you randomly, if you have quotas, but then within each quota, you randomly select somebody. And maybe even the broad, the districts themselves are randomly chosen. But this is a terrible way to do it. Interviewers choose who to survey within each quota category. And that historically favored Republicans in this country, which leads to not just error, but systematic error known as bias. And systematic selection bias. Okay. Now, here's a super popular way of getting a sample. People do this all the time. It's kind of fun. It's a self-selected sample. The researcher just publicly posts the survey on the internet, TV, newspapers. Does the DI still have one of these? They used to. And allows anyone who wants to respond. Why does that have selection bias? Should we check it out? Should we try to find one and see? Let's go to the PC and let's look at, here's one right here. Okay, you can just go to a site. Thank you, David, you put this one up. Okay, this is a great one. All right, let me make it bigger, move it over. All right, I thought you guys would like this one. Whoops. All right, iClicker. iClicker, would you rather? This is just on the internet, so let's see what we think. They just have all these surveys. Would you rather wake up naked and sore and without any memory of the night before? That kind of rhymes. Naked and sore without any memory of the night before. Next to the Burger King, telling you had it your way. Or, wake up naked next to Ronald McDonald, telling you that you were loving it. Good question. Well, we've got to vote. All right, you vote. This is A, the king, or B, the clown. All right, here we go. We'll see what you said. Anybody who wants to can vote, but this... Y'all voted? All right, looks like you did. Oh, some more people are weighing in on this one. Okay, stop, and let's see how you voted. Whoa, come on, let me vote, let me see. Oh my God, overwhelmingly the king. What's wrong with him? You loved it. You were loving it. Wouldn't you rather love it than be sore? Clowns scare you? Let's see how they voted. Okay, so let's see how they voted. How can we see how they voted? Maybe we have to vote ourselves. Okay, so we're going to vote for the clown. No, for him. 69%. You're with everybody. 161,444 votes. Overwhelmingly for the king. So you voted, oh my gosh, you're just so much, this class was almost identical. Wow, but what if we polled everyone in the country? Do you think that's how they'd choose? I don't know. You think so? I mean, probably young people are going in there. Maybe old people like clowns. I don't know. Anyway, that's a fun one. But there are other ones, like we could go to, We shouldn't do this one, should we? You want to do this one, iClicker? Okay. we're starting up. A or B? Or did you want this? Oh, you wanted this one? No base at a time like this when critical information's being, no base. Oh my gosh. Why? It's just, okay, I think it's going. Try again. The base is right here. What? And it's plugged in. Try again. I didn't change anything, believe me. You got it? Okay, I just looked at it in an angry manner. This would be an interesting one to ask on our survey because we could split it male and female. I bet the difference, I think it's going to be different for males and females maybe. Okay, we're stopping it. And I am very curious how you guys voted. Okay. No friends or slut? No friends, okay. Yeah, I mean, look at the long term. She'll get friends eventually. All right. I agree on that one. All right, let's check out what people said though. So we vote for no friends. Oh, much closer. What did we, sorry I took it away, but wasn't it overwhelmingly no friends in this class? You know why? We are 2/3 girls. And I bet the people who go on here are not 2/3 girls. There are probably more boys who go on this. You know, I bet that's it. I bet that's a sex, driven by that sex bias. Okay, so, well, CNN, let's go to one that's actually a little bit, not as fun, but more serious. There's nothing, we can do this for a survey. If you see one that really grabs you, this one? You got to tell me when to stop. I'm going real slow, and then when stop right there. This one? Boy, you really feel strongly. God or the Big Bang? Do you want to do the God or the Big Bang? Raise your hand. I can't. This one. Okay, then this one. Die and go to the worst place imaginable, but all your loved ones can live for as long as they chose, or sacrifice your friends, family, and loved ones, sending them to the worst place imaginable, but you get to live for as long as you want. This is what you want? I think we're too conflicted. We're going to do this another day. Instead, I'm going to grab your attention with a news story. How about that? Let's try that. CNN usually has something. CNN, they have a quick vote. CNN.com, breaking news. Let's see what their quick vote is right now. They change it all the time. Let's see. Last time I looked, they had nothing, which was crazy. But usually they have, whoa, wait a minute, I got to make this bigger. Where is it? This is the first day they've had nothing, so instead I have an iClicker. All right, which is one right here. All right, so our iClicker question is going to be this one. This is the one that they had. Where's our iClicker? Go to, hold on, I just got to find it. iClicker, get it started, and it's going to go. Come on, iClicker. And should should you pay by the pound? Yes or no? This was really the quick vote yesterday. I think I'm just jinxed today. I did start it. Watch. And it's not doing it. Oh, there it goes. I think it's just like people are just voting too rapidly and it's just freaking out. Okay, pay by the pound. Maybe you and your luggage together should pay by the pound. You know, you just get in. I shouldn't influence you. only talking about doing this, by the way. All right. Y'all done? I think you're all done. Stopping. All right, let's see how you voted on this one. No. 64% said no. Okay, let's see. But how many people voted all together? Did you see it was almost 300? 280? All right. About 280 people. Now we're going to see how the quick vote, yesterday's quick vote, this was on CNN yesterday, and look how many people voted. 8,720 said yes, self-selected poll. Remember, who goes to these sites? How many of you went to CNN yesterday and tried to vote on this question? But this grabbed some people's attention. And of the people whose attention it grabbed, the majority want to change the law and make it this way. There were some news articles about it. All right, now here's our iClicker question, and see which one this is. Can you even read this? I'm sorry. It says more people voted in the CNN quick vote than in our class vote. That's true. Does that mean that the CNN quick vote more accurately reflects how all US adults, all 200 million adults, would feel about this question? A, yes, because the larger the sample, the greater the accuracy. Or B, no, because neither sample was randomly selected. So both have selection bias. So both have selection bias. That's B. Does a larger sample, just because it's larger, make up for selection bias or not? If you think it does, just because it's larger, vote A. If you think it doesn't, if you think selection bias will continue even with the, just won't be canceled out, vote B. All right, y'all done. 239 people, 244 people. We're gonna stop it. Only 245, where is everybody today? It's nice out. Oh, it's only gonna get worse. This is awful. 250, okay, a little better. 1, come on, all right. Stop, whoops. I am so sorry. We'll do it again. Come on, again. So we're just gonna we're gonna stop it and we're gonna start it again. I am so sorry. I hit the wrong thing. I was looking at the numbers. Okay. Let's do it again. Go ahead, fast. No, we wanna, it's jammed. Okay, let's get up to like 240. Come on, guys. Just vote again. You'll get credit for both of them. I mean, you won't. You'll get credit for this one. I can't record the other one. Oh, it might have been recorded. I don't know. You'll get credit either way. Just vote. All right. I don't know what happened to those other people. They're not voting? All right. Just going up to a minute. All right, now, stop it. Why would I stop it before? Did it disappear and we couldn't see anything? So annoying. Okay, no, you're right. Very good. Unbelievably good. That's great. A lot of people wouldn't have answered that. That's fantastic. I'm really proud of you. It's amazing. Okay, so let's do another one. All right, let's do one more. And, all right, now we're gonna compare this one. I wanna see how you think, and this one we're gonna compare not to one of those self-selected silly polls, but to a different type of poll, a scientific poll. So go ahead, and do you think it should be legal or not for same-sex couples to marry. This is what the Supreme Court's talking about now. A is legal, B not legal, and C is unsure. Jammed, is that what this means? We'll go to 40 seconds. 40 seconds? Can I stop it? No, okay. Can I stop it now? Yes, I'm going to stop it. All right. Okay, let's see. Whoa, 81%? A whopping, only 11% think it should be not legal? Wow, okay. Now let's look at, let's get out of here and whoops, that's not what I want to do. I want to just get completely out of here. Go to, let's go to, which one should I choose? This one? Nope. All right, so, we'll go to a real, let's see, pollingreport.com. This, let's see what they have. Get rid of that thing. All right. And look at this, exactly the same question in the CBS News poll. And let's see how this news poll was done. It was conducted March 20th to 24th, just last week, 1,181 adults nationwide. And what they said was 53%, as opposed to our whopping 81%. 39% said not legal, 8% said unsure. But check this out. If you look at just younger people, like you guys are, even younger than this, you said 81% said legal. These are 18 to 29-year-olds, 73%. Look how the older you get, 73, 59, 46, 35. If you go up any higher, it's going to go down and down and down and down. It's truly amazing. Yeah. And it's just really, this issue is going to be a non-issue very shortly if the trend continues. Total non-issue. Look at that. It's amazing. So, but this is what I want to show you. Read this. Look at this. Where did they get, what is this margin of error? Do you know what that means? Does anybody here know what that means or pays attention to whether a survey has a little margin of error attached to it? Raise your hand if you pay attention to that. Raise your hand if you don't look at that. Well, you should look at that, because if it has a margin of error attached to it, you know what that is? That is 2 standard errors, just what we've been learning, standard errors for percents. And what it tells you is that we can use, that it was a random survey. We can model it with a probability model, pretend everybody in the country is in a box, well, as with yes and no's, right? Like we want to see what everybody in the country thinks about this issue. And so we randomly sample how many? 1,181 people. It's like pulling 1,181 tickets out of the giant box, and it's going to vary. Each time we choose a different 1,181 people, you're going to get something slightly different. And how much it varies is determined by that standard error. So what we can use the normal curve, we'll see in a few minutes, and we can say we're 95% sure that if we sampled the entire population, all 200 million people, adults, we would get 53% plus or minus 3%. So what does that mean? 53 plus 3 is what? Hello? 56. 53 minus 3 is what? 50. So that would be what's called our confidence interval, our 95% confidence interval, meaning we'd be 95% sure that if we polled everyone, we'd get between 50% and 56%. All right, so we'll see how that happens. But that's because this is a random poll. So let's go back to the doc camera and fill this in. This self-selected sample, as you figured out, is the worst type. Terrible. Why is it so bad? Because it has a huge, huge selection bias. We saw that. Huge selection bias because we saw that with whether you should pay by the pound, whether or not you should charge heavier people more to fly. So people who feel strongly about the issue, like people, I guess, who look over at heavy people and see them flowing out of their seats and say they should, get upset or something, people who feel strongly are overrepresented. Well, there is some rationale. It, costs more. Maybe you should do something like combine people's luggage, so a little tiny skinny person with a big luggage or a big heavy person with a little luggage, they'd be charged the same. Okay, so now we saw this probability sampling. Do you know where you're getting this deja vu feeling? I hope you're getting the deja vu feeling. It comes from random sampling, a probability sample, where everybody in the country would have an equal chance of being chosen, is the best way to get a representative sample. And this should remind you of when we looked at treatment versus control group back at the very beginning. We talked forever about how randomizing, if we want the treatment and the control group to be as much alike as possible, what did we decide to do? Not hand select them, but what? Randomize them, yes. And it's the same thing here. If we want the sample to be as much like the population as possible, we should randomly pick them the same way that we did with the treatment and control group. Otherwise, you're going to introduce bias. That's the idea. Okay? And I think that's why you got it so quickly, because we've talked about it so much before. All right, so this is the best type right here, probability sampling. See, here the interviewers chose and they introduced bias. So this and here, the people themselves, it would be like the tickets jumping out of the box. Choose me, choose me. I feel strongly about this. I want to get out of here or whatever. Okay, so this is the best type, because it eliminates selection bias. All right, I think we're good on this. We can turn the page. But it's not only for this reason. There's another, even more, just as important reason. That scribble, it said, yeah, what does that say? Eliminates selection bias. Oh yeah, that's what that says. Eliminates selection bias. Now, thank you. Probably a lot of other people couldn't read it either. So that's what I said here. Human judgment introduces bias, and random selection will eliminate that. So most likely to do that. So that's super important. But also, here's the second reason it's so important, is because we can translate, when they're random samples, oh my goodness, this whole time, oh Lord help me. Okay, random samples can be translated into box models, so we can use the standard errors that we've worked so long on these past few weeks to determine to give a measure of the accuracy of our sample. We don't just estimate, what we think the population parameter is. We can also say how accurate it is with a standard error. We can give that error bars around it. So random samples can be translated into box models so that we can use statistics and measure the accuracy. They're based on chance procedures, like gambling games. Okay, so we are almost done here, and then we can actually compute the standard errors and look at where that margin of error comes from. All right? And that's what we're going to spend most of the hour doing. But first, when I said that random samples solved all our problems and eliminated selection bias, I was overstating the case. They don't solve all our problems. They do eliminate selection bias, but there's other biases. The big one is non-response bias. What does that mean? Well, you can be selected through random digit dialing. You know, we can have an objective chance procedure to select people randomly, but are they going to answer their phones and actually give a response? How many people here, if somebody randomly dialed you, some survey organization randomly dialed you and said, hello, would you take a few minutes to fill out our survey? Raise your hand if you'd say, sure, I would, and answer the survey. Raise your hand if you just wouldn't bother. That's overwhelming. Overwhelming non-response bias. You just said, right, that's what it is. Why is that a problem? Why can't we just sample more of you? You know, it's just going to take us longer. Why would that be a problem? Let's say we wanted to get 1,000 people. And if, you know, the people, only 10% of them respond, we'll just have to sample, you know, instead of 1,000, we'll have to sample 10,000, and then we'll get our 1,000 from that. Why is that a problem? Well, it'll take us longer, but it wouldn't be a problem, would it? We just sample more people. Do you think that would work? Why? You say no, you're going like, what? It's another type of bias, yeah. The people who aren't responding, you guys, I mean, it would be fine if everybody, if people who didn't respond were just like people who did respond. That it wasn't, but look at you guys, you're overwhelmingly young. You know, you're students here, you're undergrads. And young people don't respond, whereas old people respond at a much, much higher rate. Where my mom lives, in the retirement community where she lives, I've asked people the same question. Overwhelmingly, they say they talk to survey people. So if we just, you know, waited till we got 1,000 people, we'd have a sample that was mostly old people. It wouldn't be representative at all. So how do we get around this? How do you think pollsters get around it? Because clearly they did in the last election, they did in the pre-election polls. Even with young people, they were very, I mean, they predicted the elections very well. What they do is some complicated weighting procedure so that, what do I mean weighting procedure? Weighting, like weight, not waiting in line. What they weight the responses of those of you who are really hard to reach. Let's say I call you and 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 you're never going to answer, but something happens so you finally pick it up, maybe probably accidentally or something, and then you answer the question. Well, then your response is going to be weighted more than somebody who picks it up right away. All right, so that's basically, and it actually works pretty well. So that's the non-response bias. Now what about the response bias? What does that mean? Well, I think you're probably aware of this one. Phrasing of questions influences responses. Phrasing of exam questions certainly influences responses. When I phrase a question one way as opposed to another, it can make it a lot harder. You know that with homework or anything else. And with political questions, I mean, you can certainly evoke certain emotions if you want to, and others, you know, depending on the wording. Obviously, if I phrased a question about abortion as a woman's right to choose, as opposed to killing an unborn baby, I'm going to get different responses. All right, so in other words, let's get to the next chapter. Basically, we're going to make some estimate from a sample statistic. So this will be from our sample statistic. From our sample statistic, we're going to estimate what? A population parameter not a perimeter. A parameter, we're going to try to get rid of this bias through what? Through probability sample. Well, we're going to reduce this. You can't get rid of it. We can get rid of selection bias, but there's other biases. We'll reduce this by what? Random sampling or probability sampling. And then, this is what we're going to talk about here. We're always going to have chance error. What does that mean? It just means the error due to the luck of the draw. You know, you pull 1,000 people out just randomly from the whole population. There's good, you know, your answers, your statistics are going to vary. You pull a different 1,000 people out, they'll vary again, you know, just because of the luck of the draw. Well, that, since it's a chance process, we can measure with our standard error. Okay, that's what we'll do. And we can use the normal curve as long as our sample size is big enough. So, all right, so this is the one that we're going to look at now. And we are going to, you can calculate it, only if you do random sampling though. You can calculate it by what? The standard error. So let's do that. That says calculate by the standard error, the chance error. All right. So we are going to do exactly that. We're going to estimate population percents from sample percents when we randomly, only when we randomly draw a sample. Okay? It's called inference, statistical inference, drawing conclusions about the whole population from a randomly drawn sample. Now, so far, when we've been looking at chance processes, we've been knowing, like with gambling games, we know what the odds are. We know exactly what's in the box. That's, you know, we know what the roulette wheel looks like. We know how much money we'll win and we'll lose. Not how much money we'll win and we'll lose, but we know what the odds are. And then it's just the luck of the draw. This, now, we're going to sort of go in the other direction. We don't know what the population, what the box looks like. We don't know that. All we see is one little sample that we have, just due to the luck of the draw. And from that little sample, we have to estimate what's inside the box. So we're going in a different direction, but we're going to use the same math. All right? And it's much more common to go in this direction, to have this unknown population out there, and all you see is one little sample, and you're estimating what the population is from your sample. Okay, so I wrote this a few years ago, and look, it's still holding up, 53%. Well, I might have cherry-picked that survey. There might have been, anyway, it was a real survey. It is getting more and more, you know, as I showed you, you know, older people are dying off and younger people, but in 2 years it's not changed that much. Okay, so estimate the percentage of all American adults who would favor legal recognition of homosexual marriage. Well, if 53% of our sample favors it, what do you think we're going to put down there? 20%? 53, obviously. What else are we going to write? Okay, so it's actually the expected value for the percent, and it's obviously going to be 53, the same as our sample percent. What else would we do? Okay, that's why, remember I told you there's no formula for this. Don't overthink stuff like that. Your sample says 53%, a random sample, so of course that's your best estimate of the population parameter. But give or take what amount? That's the standard error, and that is not intuitive. For almost, I don't know anybody who that's intuitive for. So now we had a sample, unlike the one that we looked at that was just done, this one only has 1,100 people. This is almost exactly the number of people who are enrolled in Stat 100. Really? We have 1,100. And there's 11, Wow. So the sample sizes for these nationwide public opinion polls are about the same size as the people in our class, as the number of people in our class, including both sections. Isn't that pretty much? Hey, boy Vaughn, wake up. I never known you to be asleep, ever.
Hey, I'm sorry.
Is it particularly boring?
No, I'm just very tired.
I mean, I'm sorry to call you out, but boy, I was shocked. Oh, well. Yeah, I'm glad you're back with us. Okay, now, so what are we going to do? We have to figure out the standard error, and I'm going to go faster because I can tell I'm boring people. When you fall asleep, that's a wake-up call to me. Whoa. Okay. So what am I doing here? What is in the box? Well, I know it's just yes or no answers. Yes or no. Do you favor gay marriage? Yes would be a 1, and no would be a 0. We're not going to include the not sure. We don't know how to do 3 categories yet. So we're going to bundle the not sure, there weren't very many of them anyways, and the no is there, and yes is here. Now, what is this box? There's going to be millions of tickets in here. The box represents the entire population of the US. So the box represents all US adults. And how many US adults are there? I don't know, over 18. I'll say about 200 million tickets are going to be inside here. 1 for every single US adult, about 200 million tickets. This exact number is not going to make any difference, as you'll see. 200 million, 2,000 million, 20 million, 20,000. We're never going to use this number, ever. It's going to be astounding, but you're not going to use it. Okay, but I just want to give you the picture. 1 for every US adult, and everybody has an equal chance of being chosen. Now, these are the yeses, favor gay marriage, and these are the no's, don't favor gay marriage. All right, now, this is what makes it so different than the gambling. We have no idea what % of these are in the population. If we did, we wouldn't be taking a sample. That's the whole reason we're taking this survey, to find out what the population thinks. So we don't know what's in there. So what do? We take out, this means that we're randomly drawing tickets out of here. Such a bad art. Little tickets we're drawing out of here. We mix this all up, the 1s and 0s are all mixed up, and then we do it through random digit dialing, but this is the idea. So we draw a random sample of size what? Of n equals, in this case, what was it, 1105. Now, do you think it's with or without replacement? All our gambling games were with replacement because the roulette wheel didn't change, the dice didn't change. But what about this? If I draw a ticket out of here, and let's say that means I got a response and somebody said, yes, I'm favoring, am I going to put that person back in and ask them again? So it's without replacement. Always, surveys are without replacement. So that's 2 differences. This, we don't know what's inside there, and it's without replacement. Always for surveys, because you don't want to sample the same person twice, because we don't want to do that. We don't want to sample the same person twice. Okay, so it's without replacement. Now, and so what did we get in our sample? Let's just write it down. So what did we get in the sample? We got 53% ones and what? 47% zeros in our sample. So that's the scenario. I'm just trying to make, that's the scenario. So now we want to figure out, the expected value is that there's 53% favoring the entire population, but give or take what? Well, that we can use the standard error for percent, which is this, right? SD of the box. Whoa, you stop right there, SD of the box. How can we figure that out? What are you going to do? Say the square root of who knows times who knows? How can we figure that out? We don't know it. If we knew it, we wouldn't be taking a survey. So we're stopped in our tracks right there. Well, anyway, let's get the formula. Over the square root of n, which would be what? That number right there, 1105. Times 100%, but then we'd be thinking again, wait a sec, we developed this formula with replacement. Think about it. If it was without replacement, theoretically, we could keep drawing tickets and drawing tickets and drawing tickets till the box was empty. Till the box was empty, which would mean we'd get the same result every single sample. If we did that for every sample, drew until the box was empty, we'd always get exactly what was in the box and there'd be no variability. So without replacement has to reduce the standard error somewhat because it's going to make it 0 at some point, so it's got to reduce it. So we got two problems, 1 and 2. We don't know the other. Okay, how are we going to deal with those? Let's think about it. Let's ignore the with or without replacement and just think about what happens if we use the sample SD to estimate the population SD. Sample SD. What was our sample SD? Let's try it and see what happens. Okay, so we're thinking about doing this, using the sample SD, which is 53% of the ones, and we had 47% of the what? Zeros in our sample. So this is our sample. Not the box, which we're supposed to use, but this is our sample. And we'll think, let's try it. Let's just use this. Well, how would we do that? So the SD of the sample would be equal to, no, we just have 2 tickets, shortcut. So we could say 1 minus 0, the numbers on the tickets, times the square root of, the fraction of the tickets that have the 1 on them, that have one of the numbers, which is 0.53, times the fraction of the tickets that have the 0. That's 47 out of 100. 0.47. They sum to 1 there. And this 1 minus 0 is really unnecessary. It's just 1 times that. It's just that. And this is very, very close to 0.5. It's almost 0.5. Now, for now, just trust me that this is gonna work. Now, how would we go about? Well, no, don't trust me. I'll show you why it works. Why it works is really fast is because we're not going to lose hardly any accuracy because in a 0-1 box, the standard deviation is this is the biggest the SD can ever get. If we had all the same numbers in there, 1s or 0s, we'd get 0 for SD. And this is the biggest it can get. Why? Well, think about it. Let's imagine pretend like we got this really weird sample, right? We have 1s, we don't know what we're doing, and 0s, and we got really unlucky. And we got huge variation between the 2 samples. Let's say sample A has 50% 1s. Sample A is 50% 1s and 50% 0s. This will really help you actually, so pay attention because you're going to be using this all the time. So keep this, let's think this through. And sample B, we get something very different. 60%, let's say, 1s and 40% 0s. I mean, if you have a really big sample, that's going to be unlikely. Like if your sample size is 100 or more, you're going to get something that's going to be really unlikely to get that big a variation. But let's say we did. Watch. The SDs aren't going to be that different. the SDs, because well, look at this SD. This SD is the square root of 0.5 times 0.5, which is what? 0.5. The square root of 25 is 5. And this one, this SD with the 60/40 is the square root of 0.6 times 0.4, which is the square root of 24. The square root of 0.24, which is almost the same thing. It's like 0.49. They're extremely close. So you don't have to worry about it very much. And in general, I want you to remember why, because this is, you should really understand this. Remember why the SD of a 0-1 box has to be, it's real simple to see, has to be between 0 and 0.5. It can never be bigger than 0.5 because watch. Why? You can see. If let's say you have a 1 and a 0, and you have a 50% ones and 50% zeros. This is the biggest it can ever be, because here you get the square root of 0.5 times 0.5, which is the square root of 25. 0.25, which is 0.25. All right, so now let's go to 60-40 split, which we just did. 60-40 split, I should do it on a calculator. And if you do a 60-40 split, you're going to get really close to it. Here, let me just do it. So we have 0.6 times 0.4. What do I get? Okay, almost 0.49. All right, and now let's do, I don't know, 70%, 30%. We'll keep going. I'll show you it's, okay, so that would be the square root of what? 0.7 times 0.3, which is what? Think like square root of 21, okay? Square root of 0.7 times 0.3. See how it's really close to 0.5 still, even with a 70% 30 split? It just keeps going down. So now you get 0.46 approximately, and the rest we can do in our head if we go by tens. Watch. 80%, 20% split. Let's do that, 80-20 split. This one is easy for you because it's the square root of 0.8 times 0.2. Think 16. Square root of 16 is 4. So the square root of this is 0.4. We can keep going. 90-10 is another easy one. That's the square root of 0.9 times 0.1, which is the square root of 0.09. What do you think? What's the square root of 9? So what do you think this is going to be?
0.3.
Thank you. You're up. Okay. Finally, what if we have 100% and 0%? You know there's no variability there. The average is 1, and there's no deviation from that average. Every number is 1. It's the square root of 1 times 0, 0, which is 0. So that's the range. All right, now you understand why this isn't going to make much difference. So let's go ahead and calculate. So we get the standard error of the percent is equal to SD over the square root of n times 100%, which is 0.5 times the square root of 1105 times 100%, and guess what we get? What are we supposed to get? So 1105 times 100. Ooh! What did I do wrong? I did 5 instead of 0.5, so that should be 1.5. 1.5%. That's our standard error. And if you notice, you'll see this margin of error of 3% for most of the polls. That's because most of them are based on sample sizes of 1,000. I can see I'm losing you rapidly. We have more to do, so I'm going to skip ahead to a this is so important, but you know what? Oh. Let's just go back to this, okay? You know what this is about? This is about why sampling without replacement and with replacement aren't going to be that different as long as our sample is only a small fraction of the whole population. But I just want to make sure while you're still awake that we can finish this problem and not sidetrack you. So can we do this a little bit later? Sound good? I want to continue with this problem. We've got the 53%. We've got the standard error of 1.5. And now I want to show you how the normal curve fits in and how we can say how sure we are of our estimate of 53 plus or minus 1.5. That's what I want to do now, and then I'll come back to this. Okay? So now we're continuing with our problem. We got 53% favoring legalization of gay marriage, and we've got this standard error, okay? Now, this is really important, so everybody pay attention now. We've got this standard error, and how can we use that? How can we use this? How can we use this to say how confident we are that 53% plus or minus 1.5% favor legalizing gay marriage? How sure are we that if we really polled every single US adult, we'd get between 53%, what does this plus or minus mean? I'm adding plus 1.5% to bring me all the way up to there, and then I'm subtracting 1.5% to bring me down to there. So this is, when I say plus or minus 1.5, what I mean is this range right here, okay? Just adding and subtracting that range. So how sure are we that if we polled everybody, they'd be in that range? Well, you know what's so amazing is because of the central limit theorem and what we learned last week and before break, we know that if this is drawing tickets at random out of a box that just has ones and zeros, that eventually, if n is big enough, it's going to look like the distribution of sample percents. It's going to look like the normal curve, that beautiful normal curve. With the true population percentage right in the middle, whatever is our true population percentage, we don't know, but it's going to be right here in the middle, the true population percent. We don't know what it is. As a z-score, we know what it is. As a z-score, what's it going to be? Zero. We don't know what it is. We don't know if it's 53%. It probably isn't. It's probably something close to it, but not 53%. We don't know what it is. But what we do know is what? We know that if hundreds and hundreds and hundreds of pollsters each took a random sample of 1,105 people, just like we did, pretend we were the pollster here, just like we did, they wouldn't all get 53%. No. They wouldn't all get the true population percent. No. But they would get a distribution around that. The most likely would be the true population percent, but that 68% of them would get sample percents within one standard error of the true population, right here. 68% of the hundreds of pollsters would get between -1 and 1 standard error of percent. And 95% would get between what and what? 2 standard errors, 95%. So let's just stop there for a minute. 95%. 68% would get between here and here, and between here and all the way to there would be 95%. All right? Now we just see one little sample. We've got this sample. Where is it? Right there. Our sample we're one of those pollsters, and we've got our little sample, 53%. Well, there's a 95% chance that we are in here just because 95% of the pollsters will be in there. 95%. So if we take this 53, I mean, pretend we're not. Pretend we got a lemon. Oh my goodness, pretend we just by the luck of the draw, we did everything right, but we're way out here. Look what would happen to us. If we're way out here, we go over, pretend we're like way out here. I mean, it's gonna happen to some people. Then pretend we're right there. That's where the 53% is. Now we go over the 2 standard errors. So we go, well, pretend we're right here. So we go over 1 standard error and another one. And then we go 2 standard errors in this direction. So that would be, we'd be 95% sure that it was in that range and we'd be wrong. And we'd be 68% sure it was in that little range. But 95% of the time we're going to be inside here. 95% of the time we're going to be inside here. So if we went over 2 standard errors in either direction, pretend we're right here, well then we'd go from here to here and it would capture the true population percentage. I don't expect you to get that right away, but sort of get the idea. We're going to talk about this a lot. So the idea is, and it's written down here, is that 68% of them would get within 1 standard error and about 95% would get within 2 standard error of the true population percent. So that's what a confidence interval is. We can be about 68% sure that the 53% plus or minus 1%, this range right here, we can be 68% sure, which isn't very, people don't like that, 68%, but that's how sure we can be that if we polled everybody, the true population percentage would land somewhere in there. But we can be 95% sure, let's try the 95% sure, that it would be within 2 standard errors. So let's do the 95% confidence interval. We'll do it way down here. We can be, how are we going to do that? We can be 95% confidence interval is going to be what? We can fill in these blanks when we do it. A 95% confidence interval is going to be our sample percentage plus or minus 2, because that goes on the normal curve with 95, 2 times the standard error for percent. So what does it mean in this case? It means that our sample percent is what? What did we get in our sample? Hello? What did we get in our sample? 53 plus or minus 2 times what? What's our standard error for percent? 1.5. 1.5, yeah. Okay, so it's 53 plus or minus that. So now we're ready to fill this in. 53 plus, whoa, these should be all plus or minus. 53 plus this 2 goes with 95%. This is the z-score. Between 2 and negative 2 is 95%. Okay, so what should we fill in here? 2 times 1.5 is what? 1.5 plus 1.5? 3. So let's do our 53, let's do the upper limit. 53 plus 3 is what? 56. That's our upper limit. And what should I put down here as our lower limit? What? 50. So that's what it means. We're 95% sure if we polled everybody, it would be in that range. That's what the pollsters mean when they put that margin of error on. You'll see it over and over and over again. They always give a 95% margin of error. Okay, that's what they mean. We're not 100% sure, we're 95. Now, what if we wanted to be 80% sure? You never see this, but I want you to get the idea. An 80% confidence interval would be what? It would be our sample percent plus or minus something times the standard error for percent. Now, what should I put in there? Look in the back of your books and see if you can figure it out. What do you think should go in there? You have to use the normal table. What do you think should go in there? Anybody want to say? Does anybody know? Just so I know you're with me, because I don't have time for the eye clicker I was going to do. Anybody want to shout it out?
1.3.
Yes, thank you. Where did I get those? Where did he get that? For people who don't see it. What? Yeah, 80%. He went down and looked. Where'd he go? 80%, right there. And then he rounded to the nearest line. So it could be 128, 129. Do you see what we're doing? Do you understand? Between 1.3 and negative 1.3 is 80%. So we're 80% sure we're one of those people. So we could go 1.3. So let's do this one. So this would be 80% confidence interval. If you want to be 80, it would be 53 plus or minus 1.3 times what? That same 1.5%. And you do it out. Let's do a 68% because we can do this one in our head. What are we going to, 53 plus or minus what? 1. This one's real easy. The upper limit will be 53 plus 1.5. And the lower limit will be 53 minus 1.5. All right? A 90% confidence interval, I know this one off, it would be 1.65 times 1.5. And that would take us from 50.6 all the way to 55.4. Let's say we wanted to be 99% tremendously confident. Is this number going to be bigger? See how this number is going to be bigger? It's going to be further out. If we want to be 99% confidence, where do we go to? We'd look up 99 in the middle and you get 2.6 times 1.5. And what would we do? We'd go up, we'd add this bigger number. We'd have a bigger interval. If we wanted to be 100% sure, it would be between 0 and 100. We'd go all the way out. Okay, so this is 49.1 to 56.9. Now, I know I'm going to put your homework up as soon as you leave this class, and we have 5 minutes left. And I'm going to go the whole hour because now I can explain to you that other page, and it's going to blow your mind, actually, if you think about it. You'll actually be amazed by it. So let's go to, whoops, I forgot part E. Part E, but I think you can, let's do part E together. Oh, okay, part E is actually kind of interesting. It says, okay, what can I apply the confidence interval to? Can I say that I'm 95% sure? Can I do that 50% to 56%? Can I do that and apply it to the whole world? What do you think? Why? Because it wasn't drawn from the whole world. Can I apply it to US college students? No, I can't apply it beyond my population, and I can't apply it to a particular subset. I can only apply it to the population that I drew from. So which one, the only one that's going to be true here is which one? The only one is going to be from the population from which it was drawn from, which was all US adults. That's the only one that's going to be true. If we try to go wider to the whole world, the whole galaxy, whatever, of course it's going to be false. If we try to go narrower, think about going to just gay people. Of course it's going to be a different percentage. So these are all false. Now the very last thing, and I know I'm rushing over these important concepts, but this one's easy for you to get. We're not going to go through all the math here, but I just want you to, I mean, you can read this and we'll go over it later, but I want you to understand this idea right here. And what this idea says is, I'll wake you up here, okay? What this idea says is you don't need a bigger sample for a bigger population. You'd think you would. You'd think you'd, for the whole world or for the United States, you'd need a much bigger sample than for the U of I. But here's why you don't, intuitively, and I'll go through the math later, but intuitively, imagine this. Imagine like, all right, I gave these giant wild New Year's Eve parties when I was a few years back. Now I'm over the hill, but giant, okay? And I'd make these giant punch bowls, huge. And the secret ingredients to them, what made the party wonderful, was, you can probably guess, it was like a lot of liquor, but tasting really like it didn't have much liquor at all to get the women all drunk. Okay, so how did I do this? Think about this. Giant punch bowls. I mean, like industrial size, okay? These were wild parties. Now, I put all these ingredients in, stirred them all up, stirred them. This is our box. randomly mixed them up, and then I had to taste it. Do you think I had to taste like bowlfuls and bowlfuls just because I had a giant? No. As long as it was well mixed, I just took a little sip and knew when it would be just perfect, just from a little taste. So what I'm saying is I didn't need giant gulpfuls, a whole giant glasses, just because I had a big punch bowl. Okay? Because as long as you take a random sample, I'll go over that more later. Okay, see you tomorrow. I'll see you after the weekend.